Hello and welcome back to Measure Theory. First, let me thank all the nice supporters on Steady. We have come very far in the series and reached now part 9. I was talking about the very important convergence theorems, and today I want to tell you about Fatou's lemma. This lemma is much more important than it sounds first. However, it's not quite a convergence theorem, more or less half a convergence theorem. But it is so general that you can apply it very often. Okay, then let me explain you what the lemma states. As always, we have a measure space consisting of a set, a sigma algebra and a measure. And we also have a sequence of measurable functions. Okay, here I want to write down the codomain of the functions, and there I have to tell you there are different possibilities. And they lead to different variations of Fatou's lemma. However, I think the best way to describe it is again to choose non-negative functions. When I say non-negative, then it's clear that the 0 is included, but it's not clear if infinity is included. However, here it is not a problem, we can just include it. And now to the statement of this lemma. Because we are in the realm of the convergence theorems, the question would be again, okay, I have an integral over x and a limit inside. Can I pull out this limit? However, Fatou's lemma is a little bit more specific. It does not look at the limit, rather than at the limit inferior. Now Fatou's lemma claims that if we look at the limit inferior of our sequence of functions fn, so here's d mu, then I can pull out the limit inferior, and then I have the limit inferior here of the numbers given by the integrals of fn. But we don't have an equality sign here, just an inequality sign. And Fatou tells us the left hand side can't be bigger than the right hand side. So you see, the lemma is not so strong as a convergence theorem, but please note that our requirements are very weak. We only need non-negative measurable maps, nothing else. The actual convergence theorem that follows from this claim here is Lebesgue's theorem, which we will consider in the next video. Before showing you the proof of this nice lemma, let me first explain what this new function lim_inf of the sequence of functions actually is. Well, of course, it is a function, which means it is defined on x and maps also into our non-negative numbers, including infinity. And now I want to give you the definition. So the function is defined for all lowercase x. And now we use what we know from the limit inferior. It is given by the limit of the infima, but cut it at the beginning. So we go from n to infinity. And then we look what happens when n goes to infinity. This is the definition of the limit inferior for a sequence of numbers. And here we just have numbers because we look at fkx. And there you see the lowest level that the infimum can have would be 0. But in the limit, of course, it could go to infinity. So we also have to include infinity. Also in the case when we would exclude infinity here, because in the limit it could happen. And because we need the infinity symbol for this function, we can just add it from the beginning. And of course, it just makes the claim stronger. The beauty of this is that we know that the limit inferior is also measurable. Simply because you can easily show that if you put in measurable functions, infima are measurable, and also limits of measurable functions are also measurable. For the whole proof now, it makes sense to use some abbreviations here. Let's call the limit inferior just by g of x. So we have a function g now, and also these functions here, given by the infima, let's call them gn of x. And of course, all the functions here are measurable. And we get another information out here. These functions here are now monotonically increasing. So G1 is less or equal than G2, less or equal than G3, and so on. This follows immediately from the definition of the infimum. Because if we shift the cut point n to the right, the infimum can only get bigger, not smaller. Okay, so we get out a sequence that is monotonically increasing. And of course, this would be very helpful for our proof now, because we can use our convergence theorem we already know. And of course you know, it's the monotone convergence theorem. And indeed with this the proof is not so long. On the left hand side we have the limit inferior, and now I write that as the limit of our GNs. Indeed, that is just our limit inferior here. And now we want to pull out the limit here. And you know now it's allowed by the monotone convergence theorem. And we also have the equality here. Please check with the last videos that we have indeed satisfied all the requirements of the theorem. Now in the next step I substitute the limit with the limit inferior, simply because this is the thing we want to talk about in Fatou's lemma. And of course here it's the same thing, doesn't make any difference at all. However, in the end we want fn and not gn in the integral here. Therefore you can ask, what is the connection between gn and fn? And then you look at the definition and see, okay, the gn is defined over all fk where k is bigger than n. And then you choose the infimum, the smallest possible value. And therefore, of course, gn is always less or equal than fn as being the infimum. So let's state that as we know gn less or equal than fn for all n. And now you want to use the monotonicity of the integral, which is a very nice property of the Lebesgue integral. So if we have the inequality here, then it also holds for the integral. Okay, so this inequality we now want to use here on the right hand side. So let me summarize what we have here. The left hand side is the limit inferior inside the integral. And on the right hand side we can use this inequality. The limit inferior conserves the inequality, which means we have here less or equal and limit inferior outside. Fn d mu. And there we have it. That is Fatou's lemma. You see, the proof was not so hard and not so long because we could use our monotone convergence theorem here. Okay, so I hope you learned something today, and then you will see in the next video how we can apply Fatou's lemma. And then we can finally prove one of my favorite theorems. Okay, I wish you a very nice day and see you next time. Bye.